All right, number 4. This is the back page of the morning review for Chapter 2, Chapter 2 Derivatives, morning test review. All right, back page, number 4. Find d2y over dx2 for f of x. Now, this notation is asking us to find the second derivative. So we first need to find the first derivative, and then from there we'll move to the second derivative. So if we want to find the first derivative of f of x, in other words f prime, or in other words dy dx, notice we have numerator and denominator, so we have to go through quotient rule. Probably the most efficient way is going through quotient rule. So f prime g minus f g prime all over g squared. So f prime is the derivative of the numerator, so that becomes 1 times g, so that's x plus 2, minus the top function, original top function, so x minus 1, times the derivative of the denominator, so x plus 2's derivative is simply 1, all over denominator squared. We can distribute and combine like terms here to simplify. So x plus 2, distribute the 1, negative x plus 1, and now combine like terms. The x's cancel out. We're left with 3 over x plus 2 quantity squared. Okay, so we found our first derivative. Next step is to find the second derivative. Now, we can go through quotient rule again, but something that could be a little more efficient, a little faster, is if we simply move this entire denominator to the numerator, and then we can just rely on power rule and chain rule. So this x plus 2 quantity squared comes up as x plus 2 quantity to the negative 2. So I'm just rewriting our first derivative. All right, so now to find the second derivative, I can simply apply chain rule. So chain rule, I'm going to take care of the outer function's derivative. So bring the negative 2 down, keep the parentheses, subtract 1 from the exponent, and then multiply by the inside function's derivative. So the derivative for x becomes 1, and then 2 goes to 0, so times 1. So really, the derivative is not going to affect the final result. All right, so now try and combine this together. So 3 times negative 2 times 1 is negative 6. The x plus 2 to the negative 3, we can bring this back down to the denominator, and turns into negative 6 over x plus 2 cubed. All right, number 5, position of the particle is given by x of t, for t is greater than or equal to 0. All right, so part A, find when the particle is moving to the left. So to determine when the particle is moving to the left, we need to have some boundaries. We need to kind of know where the particle is at rest. So we first need to find some critical points. So critical points is where velocity is 0. So we're going to set find the velocity function and set that equal to 0. So I have the work here. To go from position to velocity, we can go through power rule. So t cubed becomes 3t squared. 9t squared becomes 18t. 15t becomes 15. 3 goes to 0. And we're going to set this equal to 0, set the velocity equal to 0. I can factor out a 3 and continue factoring. And then when I set both parentheses equal to 0, I get t equals 1 and t equals 5. So we have there our critical points that we can put onto our sign line, our velocity sign line. So we have 0 to indicate that as a starting point, and then 1 and 5. Okay, so to determine when the particle is moving to the left, we're going to test each of these intervals and decide when which interval has negative. Okay, because positive represents moving to the right, negative represents moving to the left. So here I can choose a value between 0 and 1, which is 1/2. If I plug 1/2, I plug into the velocity because I'm trying to determine which direction this particle is moving. Okay, so if I plug 1/2 into the velocity function, plug into the factor form is a little bit easier to evaluate. We don't really care about what the velocity value is. We just want to know whether this time value of 1/2 will produce positive or negative velocity. That's all we care about. So if we plug 1/2 into t, 1/2 minus 5 is negative value, is negative. 1/2 minus 1 is also negative. So negative times positive will give us positive. Okay, here a representative value I can choose between 1 and 5 is 2. So plug into the factor form. 2 minus 5 is negative. 2 minus 1 is positive. Negative times positive will be negative. Okay, in this interval, I'm going to choose a value to the right of 5, so I can choose 6. So plug 6 into the velocity function. All we care about is whether it's positive or negative. 6 minus 5 is positive. 6 minus 1 is also positive. Positive times positive is positive. So the interval where the particle is moving to the left will be negative, where velocity is negative. So velocity is negative between 1 and 5. Okay, velocity is less than 0. Part B is speed increasing or decreasing at t equals 2. To determine where the particle, or when the particle has increasing speed or decreasing speed, we compare the signs between velocity and acceleration. So, hey, again, just to remind you, to recap, if velocity and acceleration have the same signs, speed will be increasing. When velocity and acceleration have opposite signs, then speed will be decreasing. So that means we also need to find the acceleration function. So I'll have the work here as well. To get from velocity to acceleration, we can find the derivative. So 3t squared becomes 6t, negative 18t becomes negative 18, and then 15 goes to 0. So we're going to plug 2 into both velocity and acceleration and compare their signs. So if we plug 2 into the velocity function, so 2 minus 5 is negative, 2 minus 1 is positive, negative times positive is negative, so we know velocity of 2 is negative. A of 2, so if I plug 2 into the t value, 12 minus 18 is also negative. So notice both velocity and acceleration are negative, and both are negative, so they have the same signs, therefore increasing speed at t equals 2. Okay, find average acceleration. All right, so notice average acceleration is simply the change in velocity over change in time. Maybe the tendency that students want to do is find the acceleration at 0 and find the acceleration at 2 and then average between those two. So that's not quite what this is asking for. This is asking for what is the change in velocity over time between these two intervals. So we have to get used to interpreting this correctly. All right, so average acceleration between two endpoints. We're going to find velocity at 2 and find velocity at 0. So plug 2 into the velocity, plug 0 into the velocity. We're going to get negative 9 for v of 2, and v of 0 will be 15. Okay, we're just plugging 2 and 0 into the velocity function, either the factored form or the original term expression. They're all adequate. All right, so we can say v of 2 minus v of 0 over 2 minus 0, so that's negative 24 over 2, which is negative 12 units per second squared. Okay, acceleration has this unit of measure. Okay, where's the particle located when the velocity is 0? All right, so we can set the velocity equal to 0. And then once we find those time values, we can plug into the position to find out their physical location. So velocity is 0 at 1 and 5. We found that from part A. So we can plug 1 and 5 into the position functions, or x of t. I use s of t here, but we can use x of t as well. So a lot of times x of t and s of t are the most common notations for position. Okay, so I should have used x here. All right, x of 1. Plug 1 into the position function, we're going to get 10. Plug 5 into the position function, we'll get negative 22. So those are the positions when the velocity is at 0, or when the velocity is 0. Find a particle's displacement. So displacement is simply the end position minus the initial position. So we find s of 3, plug 3 into the position function, we're going to get negative 6. Plug 0 into the position function, we'll get 3. So the end point minus the initial point, negative 6 minus 3 is negative 9. Okay? Find the particle's distance from 0 to 3. So to find a particle's distance, we're going to involve the positions at the endpoints, but also the position when the particle changes direction. So if we look here, between 0 and 3, the particle will change direction at 1. So we have to locate that position so that we can make the correct so that we can be able to find uh, uh, the total distance correctly. All right, so we know S of 0 is 3. We know S of 3 is -6. We found that from part E. And then S of 1, okay, this is going to be we have to find and identify the point where the particle changes direction. So plug 1 into the position function. We'll get 10. So we're going to have to find the distance between each of these intervals. So between 0 and 1, this particle will move in the forward direction, will move to the right, but then between 1 and 3, it's going to start going back where it came from. So it's going to go back to the left. So we have to make sure that's why we have to find the point where it changes direction so that we can keep track and make sure that we keep track of, make each of those distances positive. Okay, between 3 and 10 has a distance of 7. Between 10 and -6, there's a distance of 16. So he's going to particle travel 7 units here, 16 units here. So 7 plus 16 is 23. Okay, for G, is the velocity increasing or decreasing? So we have to be able to interpret this correctly here. Velocity increasing, in other words, this is asking for the rate of change of velocity. Rate of change of velocity is acceleration. So this is asking, is the acceleration positive or negative at t equals 2? Okay, so if we plug 2 into the acceleration, okay, so plug 2 into the acceleration, we'll get -6. 12 minus 18 is -6. So -6, so we know acceleration is negative at 2. So since acceleration is negative, we can say velocity is decreasing at t equals 2. Part H, find the velocity and position when the acceleration is 0. So we can find the time when the acceleration is 0. So we take the acceleration function, set that equals 0, t equals 3. Now we can plug 3 into the velocity and the position function to find the corresponding answers. So plug 3 into the position function, or x of 3, we'll get -6. So plug 3 into the position function, and then also plug 3 into the velocity function, and we'll get -6 as the position and -12 as the velocity. All right, some practice problems involving quotient, chain, and product rule, number 6 and 7. So find dy dx, so find the first derivative for f of x. Now, if you look at f of x here, f of x, notice that these two expressions, or these two terms, are related to each other by multiplication. So we have to involve product rule. And also we have to involve chain rule, because we see parentheses with multiple terms with an exponent outside. So eventually we're going to get to chain rule. So product rule first, and then we can get to the chain rule when we get to that point. All right, so the rule for product that we're going to apply is product rule, f prime g plus fg prime. So f prime, I'm going to rewrite this as rational exponents. So square root of x, I'll write it as x to the 1/2. I'll let this represent the f function, and then this represent the g function. So we're going to go through product rule here. F prime g, so f prime is the derivative of x to the 1/2. We go through power rule, so 1/2 x to the -1/2 times the original g function, so x cubed minus 7 to the 4th. Okay, plus, we're ready for the second portion of the product rule. F is the original first function, so x to the 1/2 times g prime. So here is where we have to involve chain rule for this portion, x cubed minus 7 to the 4th. So let's take care of the outer function first, which is the 4. So the derivative of this portion is we take care of the outer function first. So bring down the 4, keep the parentheses, subtract 1 from the exponent. So 4 minus 1 is 3. Multiplied by the inside function's derivative. So whatever is inside the parentheses, we have to make sure we also include that as part of the chain rule's derivative. X cubed becomes 3x squared. -7 becomes 0, so that just drops out. So we have this entire expression that represents the derivative. So we're going to try and clean this up as much as we can. Negative exponent, I'll bring this back down to the denominator. The 2 will share the same denominator space as the root x. And then the x to the 1/2, I can combine the x to 1/2 and x squared, multiply the bases by adding exponents. So 2 plus 1/2 is 2.5 or 5/2, and then 4 times 3 is 12. So this is probably as far as I can go with to find f prime. Okay, number 7, find dy dx for f of x. So here, the way that this is these expressions are related to one another is by division. Okay, so we'll use quotient rule. So quotient rule, I'm going to rewrite the top portion as 2 minus x squared to the 1/2. And again, we have to involve chain rule because we have binomial with an exponent outside. So chain rule, quotient rule first. So f prime g minus f g prime all over g squared. Okay, we'll let the top function represent the f function, and then the bottom represent the g. So first portion is the f prime. So f prime requires us to find the derivative of the top. So 1/2. We take care of the outside function's derivative first, which is the parentheses to the 1/2. So bring down the 1/2, keep the parentheses, subtract 1 from the exponent. 1/2 minus 1 is negative 1/2 times the inside function's derivative. So we look inside the parentheses, the 2 goes to 0, the negative x squared becomes negative 2x. So this whole portion represents f prime. So f prime, we found that, times the g function. So the g function is the original denominator, so that's the 4 plus 3x, minus f is the original top function, so 2 minus x squared to the 1/2 times the denominator's derivative, so g prime. So the derivative for 4 plus 3x, 4 goes to 0, 3x goes to 3, okay, all over the denominator squared, so 4 plus 3x quantity squared. All right, from here, it's just a lot of algebraic steps to try and clean this up as much as we can. If I write this as, if I combine the terms here, the 2 and the negative, well, 1/2 and negative 2x will cancel out. The x and the 4 plus 3x will go up to the numerator, and then this 2 minus x squared to the negative 1/2, we can make this make this to be the denominator of this numerator portion, minus 3 square root of 2 minus x squared all over denominator squared, so that's just the 4 plus 3x squared. Now I have a complex fraction here. I'm going to undo this complex fraction by multiplying everything through by this root 2 minus x squared. If I distribute every term through with the root 2 minus x squared, that will allow this portion to cancel out and then distribute this portion to the rest of the expression. All right, so I'm going to multiply this entire derivative expression by 2 minus x squared to the 1/2, or root 2 minus x squared. Okay, I'm multiplying numerator and denominator by the same value, so I'm not changing the overall expression. Essentially, I'm multiplying by 1. So if I distribute this to every term in the numerator and denominator, if I distribute this term to the first fraction, notice that these will cancel out. We're just left with negative 4x plus or minus 3x squared. After I distribute, that's what's left over, just that numerator portion. Minus, and if I multiply these together, the two square roots will just become, square root times square root will just be the expression inside the square root, so it'll just become 2 minus x squared. And then the denominator here, 4 plus 3x squared times 2 minus x squared to the 1/2. These are not like terms, so the best we can do is just put them next to each other. All right, so denominator, there's not much more we can do to simplify, but the numerator we can distribute, combine like terms a bit more. And if I distribute the negative 3 through, I'll get negative 6 plus 3x squared. And then if I combine like terms, this is probably as far as I can get, negative 4x minus 6 all over this denominator expression.